Okay, so we've got a review in front of us that we're going to hit up. This covers chapter 7, 8, and 9. So as we go through this review, I will also tell you where these questions are coming from, because it doesn't necessarily go in order of chapter 7, chapter 8, chapter 9 questions. They're all kind of mixed in. So I'll give you a heads up on different questions as we go through. Most of this we will run through StatCrunch, very little hand work that we will have to do, if any. Okay? So, starting with question number 1. A simple fill in the blank. So the null hypothesis is always a statement about who? It's always about your population. That's right. Null hypothesis is always based on that population. There you go. And that was coming from 8.1. The next question is coming from 7.1. So in statistical inferences, measurements are made about a blank and generalizations are made about a blank. So it's either population or statistic. So what are the measurements made about? No. Measurements are made about the sample. Generalizations are made about your population. We're finding measures with a sample. And then, absolutely, that's right. You take the sample, you find some measurements, and then from there, we make generalizations about what's going on as a whole, overall. Okay? And that was coming from 7.1. All right, so this one is straight from 8.1, talking about your hypotheses. So a research hospital tries a new antibiotic scrub before surgery to see whether it can lower the rate of infections of surgical sites. The old rate of infection is 2.3%. The null hypothesis is the proportion of infections, the null hypothesis is that the proportion of infections is 0.023. You can see that there, P equals 0.023. Report the alternative hypothesis and in symbols. Okay. So we've got 6 choices for the alternative hypothesis. It's definitely A, because the key up here, it says that we want to lower the rate of infections. Okay? So we need something down here that says that we are going to lower the rate, and that's this guy. We want to be less than. And the rest of them, they just don't make any sense according to what's going on. So then down here, it says report the information. So is it going to be P or P hat? It's going to be P. Good. And then the symbol, will it be the less than, the greater than, or the not equal to? The less than. Good. There we go. So keep an eye out for some of those main words, like when you see lower than, decreasing, less than, things like that. You see the words greater than, increasing, more than, then we want to look at the greater than. If you don't see any of those words and it just says, are they different or is there a change, that's your kind of not equal. Okay? So be on the lookout for those words that help you out with those symbols, because that hypothesis is super important for us. All right, question number 4. It is coming straight from 8.1 as well. Again, we're still kind of talking about those hypotheses, and we're also going to talk about that Z statistic that's down below. So it says, according to a reputable magazine, the dropout rate for all college students with loans is 30%. Suppose that 98 out of 300 random college students with loans drop out. Complete parts A and B. All right, so part A says give the null and the alternative hypothesis. All right, so we'll get to the StatCrunch. It'll help us out. But we got to get our null hypothesis. What is our null hypothesis going to be? going to be about the population. What do we know about our population up here? Nope. It's the 30%. The 98 out of 300, that's your sample. But what we know about our population is right here. All college students with loans drop out about 30%. So what is this null hypothesis, this H naught, going to be? So what's in the first blank, though? Remember, you got a choice here. Is it greater than, less than, equal to, not equal to? Equal to. It's going to be that equal to. Your null hypothesis, your H naught always has equals. And then what's it going to be over here? What's your number now? 0.3. Good. Because we never put it in as the actual percent. It's the proportion. So that's 0.3. So then now we get to the alternative hypothesis. So if we go back up here, they're talking about that the dropout rate is not 30%. So what would that look like? What would it be? Greater than, less than, equal to, not equal to? The last one, the not equal to, absolutely. Because we're not asking did it lower or did it increase. We're asking that it's not 30%. Okay? So what will go into our second blank there for the alternative hypothesis? 0.3 again. Yeah, your numbers right there should not change. Your numbers should not change. All right, then from here it says find the Z statistic. Find the Z statistic. So how are we going to do that? There is a formula for it. Do you remember what that formula was? Nope. Or the other thing that you could do is we could go to StatCrunch, right? Do a little bit of running. Okay? So where would we go in StatCrunch? Stat. Okay? Proportion stats. Okay? One sample. You got it? With summary. Perfect. So we can find our number of successes. How many were there? 98. Okay. 98 out of 300, you said? And change that 0.5 to a 0.3. And is this symbol correct? Yes. Yes. Compute. What is our z-score? 0.3? No, that's the p-value. 1.00, I think it says 3 decimals, right? 4. So 1.0079. There we go. So 1.0079. Cool beans? Nice work, boys. But yes, there is a formula. If you want to know the formula, let me tell you. Again, this was coming from 8.1. So that formula from 8.1 would be Z equals your p hat minus your p naught divided by your standard error, where your standard error is equal to your p naught, 1 minus p naught, divided by n. Okay? Remember, p naught represents the value of p from your null hypothesis. So that would be the 0.3. And the p hat, that represents what happened in our actual sample. So that 98 divided by the 300 is that p hat. N represents your sample size. So you could also run that formula if you wanted to. Okay? All right. Question 5. Moving on. So question 5, this one comes out of 8.2. 8.2. So says, suppose researchers are testing people to see whether the rate of use of seatbelts has changed from a previous value of 87%. Suppose that in a random sample of 500 people, they see that 445 have seatbelts fastened. So the question is, which picture below shows the correct p-value for this? So let's think about our test statistic, because if you know what our test statistic, sorry, not test statistic, excuse me, our hypotheses are, we know whether we are a one-tail, like part A, or a two-tail, like part B. So, based off of this information up here, what is our alternative hypothesis going to be? Is it going to be the not equal to, the greater than, the less than? What do you think based off of this information? It's going to be a not equal to, because they want to know if it has changed. So that means it is not the same anymore. So if you are a not equal to, which picture represents that? It has to be the two-tail. Whenever you're not equal, you're a two-tail picture. So we know it has to be B. We know it has to be B. Okay? So when we go down here, it says graph B is the correct figure, because we just talked about that. Because the alternative hypothesis should be one side or two side? Two side, because we just talked about that. Whenever you are not equal to, you are always a two-sided. And the reason that we chose that is because it has changed. That's what we want to know. Cool? All right. Number 6 is coming from 8.3. So they're giving you some z-scores down here used in a two-tailed alternative hypothesis. Okay, they want to know which one will produce the smallest p-value. Okay, sure, Antonio. You got it. Yeah, absolutely. So look at the highest z-score, because the higher the z-score, that means the smaller the area, right, under your curve, because that's what the p-value is measuring, that area under the curve. And we want to make it as small as possible, so that means we want to be as furthest away from the middle, right? So, Antonio, you're absolutely correct. The higher the z-score, the smaller your p-value. So which one is it? It's going to be B. This is the highest value right there. 3.15. Don't worry about the negative sign. That just means we're down, like down on the negative side. But the highest value up here is B. That is the biggest z-score that we have. That will produce the smallest value for us for P. When you're looking at the number, no, the signs doesn't matter. Okay? When you're thinking about which one will produce the smallest p-value. Okay? Now, the signs do matter when we're talking about finding the area under the curve and we're actually looking at it, you know, because that will tell you which side of your normal curve you're going to be on, things like that. All right, so now we're explaining. So which one was what Antonio said? The larger the z-score, the smaller the p-value. Which one up here explains that? D. Because we want to be furthest away from 0, which means that's the mean. You're right in the middle. We want to be furthest away from 0 to create the smallest area possible. So definitely D. All right, question number 7 is coming straight from 8.3. So question number 7 from 8.3. All right, so again, kind of just talking about some things. So it says, when a person stands trial for murder, the jury is instructed to assume that the defendant is innocent. Is this claim of innocence an example of a null hypothesis, or is it an example of the alternative hypothesis? So it's about the null, absolutely. Because in the beginning, you have to assume you are innocent, right? As it always says, you are innocent until proven guilty. So we know it's about the null, so right away we know it's either B or C. So which one is it going to be? Say it again. B, absolutely. Because you are innocent until evidence tells us otherwise. So until our evidence tells us to either reject or do not reject, right? Okay. Question number 8 is coming to you from 8.4. Question number 8 is coming to you from 8.4. All right, I'm not going to read a lot of these names because those are some crazy names. So it says, a study reported that the results of a randomized trial of whole body cooling, which of course I can say hypothermia, I know that one, but the next one a little bit tougher for me, for brain problems in babies due to a lack of oxygen. 27 of the 92 infants randomly assigned to hypothermia died, and 44 of the 99 infants in the control group died. So we're going to complete parts A and B. So it says, find and compare the percentages that died for these two groups. All right. So the percentages that died in the treatment group. Who's the treatment group? The 27 out of 92. The ones that got assigned to the hypothermia. Okay? So we need to know the percent that died. How do we do that? Yeah, just divide, right? Take the 27, was it? 27 divided by 92, and it says round to 2 decimal places. 29.35. Okay. And it is the percent, so we don't have to turn it all the way into its decimal of 0.2935. So keep an eye on those little symbols there. All right, the percentage of babies in the control group. So that was the 44 out of the 99. So what is that? 44 point. Yeah, but it still wants you to round to 2 decimal places, right? So 44.44%. Yes, it is a repeating 4. Absolutely, I agree with you on that. Okay, so the death rate was greater for the babies in the blank group. Control, obviously. They had the bigger percentage. Everyone good so far? Makes sense? Yeah, you just do some quick division, get your percentages, and then just look at which one had the bigger mortality rate. All right, so now we're actually going to test. So the test hypothesis is that the death rate was less for those treated with hypothermia at a 0.05 significance level. Let P1 represent the proportion of babies with problems that would die after receiving hypothermia, and let P2 be those babies that would die within the control group without treatment. So down here, your null hypothesis, H0, who's it going to be? The control group? Well, you got choices. You got to be careful. You are comparing two guys. This is coming from 8.4, so we are comparing two populations. P1 less than? No. Equals. Your null hypothesis is always equals. Yeah, no numbers. So this is P1 equals P2. It's going to be a drop-down menu for you on your test. Okay? So it's always going to be equals. All right. Now the question is, what's the next guy? Less than? How do you know? Yes. We want to see that the death rate was less. Okay? You got those key words that I told you to keep out, or keep a lookout for. So absolutely. P1 less than P2. Everyone good so far? All right, so now it says find the test statistic for this, the z-score. All right, how are we going to do that? How are we going to find that z-score and then that p-value? StatCrunch, right? Let's go up into that StatCrunch. Okay, StatCrunch. We'll get rid of that information. Stat, what are we going? Calculators? No. Not progression. Proportions. To sample. With summary. There you go. Oops. And all we got to do is put in our information. All right. So, who was our P1? 27 out of 92. Perfect. Who's P2? 44 out of 99. Now, remember they write it differently in StatCrunch. Okay? So let's go back real quick and talk about this. So, if we had P1 equal to P2, what's the other version I told you that this would look like or could look like? It is an equation. There's an equal sign. This side has 0. And what's over here? P1 minus P2. Because all they did was like pick this P2 up right here and just moved it to the other side by subtraction. So remember that all of our other guys that look like this, or the greater than, or the less than, the sign still stays the same. All that happens is we just shift the P1 and the P2 to the same side. So all of those will still say the same way, not equal to, greater than, less than, but it will look like that. So they're still the same. They just put the P1 and the P2 on the same side. Yeah, just a little bit of algebra manipulation. Absolutely. So when we come back to our StatCrunch, we're doing hypothesis testing, so it's selected. Is the 0 okay for the null hypothesis? Yes. Is the not equal to okay? So it has to be a less than, right? Because that was our original alternative hypothesis symbol. So yeah. Oh, let's make sure I select less than. And now we're ready to go. Compute. And now you have everything that you need. Now we know our z-score, our z-statistic, and we also had the p-value, which we need for the next question as well, too. Okay? So it says for the z-score, we need 2 decimal places. For the p-value, you need 3 decimal places. So I'll give you a moment to write that down. Then we'll go transfer this information over to the other side. So what is our z-score, our z-stat? Negative 2.16, because that 7 says, hey, 5, go up 1. What is our p-value? There you go, 0.016, because the 5 says, hey, 5, go up. Okay? So we'll go transfer that information in. So our z-score, you said, was negative what again? 0.16, and our p-value was 0.0. All right. So, conclusion. Do we reject or do not reject the null hypothesis? Say it again. Reject, right? Absolutely. We got to reject. Oops. I don't know why I put a G. we have to reject because the death rate for the babies treated with hyperthermia. So what can we say? Was actually less than. Right? And the reason why we rejected, because this value right here is smaller than the significance level of 0.05. Okay? All right. Number 9. So again, kind of another question coming from 7.1 about parameters and statistics. So it says, explain the difference between a parameter and a statistic. So, which one is it? Say it again. C? Okay. Anyone disagree with that? Nope. I agree. A parameter is a measure of the population. A statistic is a measure of a sample. Okay? Cool, cool. Number 10. Again, also another one from 7.1. So explain the difference between a sample and a census. Every 10 years, the U.S. Census Bureau takes a census. What does this mean? You think it's C? So a sample is a collection of people or objects taken from the population of interest. I agree with that. A sample is definitely taken from our population of interest. Okay? A census is a survey in which every member of the population is measured. Absolutely, that is a census because you collect from everyone. And that's what the U.S. Census Bureau hopes to do. They take a census, it conducts a survey of all people living in the United States. A census means you want everyone in on that. So definitely. And if you look at some of the other ones, they just don't make sense. Up here in Part B, it says a census is a numerical value that characterizes some aspect of a sample. No. The census is a collection of people or objects taken from the population of interest. No. It's about all of the population. And then if you look at D, a census is a survey in which every member of the sample is surveyed. No. It's not every member of a sample surveyed. That would just be my sample. So, yeah. Census is about everybody as a whole. All right. Question 11, coming from 9.1 now. 9.1. Remember in 9.1, this was all about kind of reviewing all those statistical ideas and parameter ideas that we talked about from 7.1 through 8, chapter 8. So it says the mean GPA of all 6,000 students at a college is 2.85. A sample of 200 GPAs from the school has a mean of 2.19, which is mu and which is x bar. So what do you think? B? So the mu is 2.8 and the sample is 2.19. I agree. Because remember, the Greek letters go for parameters, populations. And this number right here is definitely about the population because it says all 6,000 students. Okay? So we definitely know that that number has to be a parameter. And then it says a sample. Well, obviously that means that the next number has to be a sample because that matches up with the word sample. So again, Greek letters go with parameters. Mu. We had sigma. Okay. X bars, lowercase s's, English letters go with your statistics. So absolutely, when you guys said it was B, I agree. All right, number 12. Number 12 is coming to us straight from 8.4. 8.4. All right, so it says make the two given tables into one table by combining men for capital punishment into one group, men opposing it into another, women for it into one group and women opposing it into another. The student who collected the data could have made the results misleading by trying persuasion more often on one gender than the other, but it says she did not do this. She used persuasion on 10 of the 20 women and 15 of the 30 men. So let's complete our parts. All right, so here's our information. Top one's about men, the bottom one's about women. So we got to fill in our table. We got to combine this information. How many men were for capital punishment? 20. How'd you get 20? Yeah. Add those two guys together. Gives you 20. How many men were against? 10, right? Because you take the next two numbers. Add those two together. That's your 10. Okay? How many women were for capital punishment? 9. Because you take and add the 3 and the 6. And then how many women were against capital punishment? 11. Good. Because you add the 7 and the 4. So there's your first part. We filled in our table. Okay? Now it says what percentage of men supported capital punishment and what percentage of women supported capital punishment. So of the 30 men sampled, what was the percent that supported capital punishment? And it says round 1 decimal place, so say that again for me. 66.7. Okay. Yeah, because it's a 6 repeating. And then what percentage of women supported capital punishment? 45. So we take the 20 and divide it by the 30, because there were 30 men total. And then we take the 9 divided by the 20 women that were sampled. Okay? And there's no decimal on the 45? Okay. Okay, perfect. Just wanted to double check. All right. So it says, on the basis of these results, if you were on trial for murder and did not want to suffer capital punishment, would you want men or women on your jury? So you want women? Would be preferable as a blank percentage of them are not in favor. Careful. A lower percentage. Their percentage was lower. If you chose the higher one, then that means you're probably going to go to jail for capital punishment. Okay? So yeah, you chose the lower one because you want more sympathetic vote. Everyone good? Okay, our next question, number 13, is coming from 7.2. Coming from 7.2. And this is that kind of same information that we talked about in class when we talked about the golf example. And then I think in your assignment you had one about the rifle example as well too. So we're just going back to that information about precision and bias. That's what this question's about. So if a rifleman's gun sight is adjusted incorrectly, he might shoot bullets consistently close to 2 feet left of the bullseye target. Draw a sketch of the target with the bullet holes. Does this show a lack of precision or bias? And then part B, you're going to draw a second sketch of a target if the shots are both unbiased and precise, having little variation. The rifleman's aim is not perfect, so your sketches should show more than one bullet hole. Okay? So, the first one is, which target shows us bullet holes consistently close to 2 feet left of the bullseye target? B. Absolutely. It's B. So now, does this show a lack of precision or bias? Ooh, I had it split. I heard precision, I heard bias. It is actually bias. Bias is like you trying to hit the target dead on in the center. Okay? Bias is trying to hit that dead center. Precision is the grouping of your bullets. So our grouping is good. We're just not hitting the center, which is the bias part. Okay? The more unbiased you are, the more on target you are. Yeah, you could think of bias as accuracy. Absolutely. So think of bias as your accuracy. Precision is your grouping. Like if you look at A, that is not precise because the bullets are scattered. Where when you chose B, your bullets were more close together. Make sense? Yeah, D is one that is both. And that would be the last question. That's your last guy right here. So, which picture shows both unbiased and precise? We're back to B. Because that's where all my bullets are in the middle and clumped together in the middle. Yeah. Unbiased. The more biased you are, the further away from the accuracy. Yeah, the first time it was bias. Someone's using a little bit of persuasion in their stuff. Okay? Wanda, does that make sense? You're okay? All right. Number 14. I think this is the only one that I actually went in and used a formula on. Yeah, this is the only one that I used a formula on. And for your standard error, and that formula that we'll use, I'll write it down here. This is the only one that I actually had to use a formula. And that formula, SE equals the square root of P parenthesis 1 minus P all over N.
So that's the same, like what you did earlier with Stack Crunch. You could put this on.
I don't think Stat Crunch will help you on this one. That's why I had to put that information up there. Yeah. So you just got to run your formula. Yeah. All right, so let's start on this one. So according to a candy company, packages of a certain candy contain 24% orange candies. Suppose we examine 350 random candies. What value should you expect our sample percentage of orange candies to be? 24%, right? And this one, did I tell you what section this is coming from? I don't think I did. This guy is number 14, so it is coming from 7.2. So 24%. We should expect 24% of the candies in there to be orange. Okay? So now we're going to find our standard error. We just apply our formula. But again, we can't use the percentage. What do we got to use? The decimal. So you're going to your calculator, and what are we putting in for P? 0.24, 1 minus 0.24, all divided by, what is our N? 300? 350, yeah. And that's where you're going to get your answer from. So we just run our calculator piece of information for this. 0.023. Sounds good. And so down below it says use your answers to fill in the blanks. So we expect blank percentage, 24%. Give or take what percent? 0.23? 2.3. Move the decimal twice. You said 0.23, but it's 2.3. Move the decimal place twice, Chris. Just go 1, 2. There you go. Or multiply it by 100 in your calculator. All right. Everyone good? Okay. Ooh, Chris, you had me worried there for a second.
That I had difficulty with yesterday is because it asked me, it had p hat, that you had to change it from p hat.
Yeah, you might have p hat in there because you might not know the population mean or the population proportion. Yeah, you might have p hat in there. It's possible. Okay, so 15, we are jumping into 7.4. All right. So it says, using technology, we need to complete the following sentence. I am 95% confident that the population proportion favoring the death penalty is between blank and blank. Okay? 0.594 and 0.637. Because that's coming from your confidence interval right there. Okay? So then the question is it plausible to claim that a majority favor the death penalty? Explain. B, you say yes. It is possible because the confidence interval contains values above 50%. And I agree. I agree. Because if I change this 0.594 to a percent, that's 59.4%. And that's definitely above 50%, which is considered a majority. Absolutely. There you go. Any questions on 9.1? Or sorry, 15? Number 16 is 9.1. 16 is coming straight from 9.1. And again, it's asking us about parameters versus statistics. A lot of those kind of questions coming at you. So it says a study of all the students at a small college showed a mean age of 20.7 and a standard deviation of 2 years. Are these numbers statistics or parameters? What do you think? Say it again. D, the numbers are parameters because they are for all students, not a sample. I agree. Because right up here it says all the students. So absolutely. The numbers are parameters. Okay? Now it just wants to know who is who. So what symbol would you use for the 20.7? They said it was the mean, and it's a parameter. Mu. That's that guy. Mu. And then what symbol would you use for the standard deviation of 2? Yeah, the little circle with a little tail on the end. Sigma. Sigma. Yeah. Greek letters is what you wanted to use for this because it's all about parameters. Okay? Everyone good on 16? Cool. 17. All right. So again, same thing again. 9.1. So it says a survey of 100 full-time students at a large university showed the mean number of semester units that students were enrolled in was 11.2 with a standard deviation of 1.6 units. So are these numbers statistics or parameters? Why is it definitely a statistic, Antonio? Because it's a survey, right? It's a sample. Okay, that's not all the students. So who would this be then? B, these numbers are statistics because they are estimates and they are biased. So these numbers are biased? No. No. It would be A. Yeah. They're not biased. It's not biased by any means. I mean, it's not a biased question. It's just going up, hey, you're a full-time student, so how many credit hours are you taking this semester? hey, you're a full-time student. How many credit hours are you taking this semester? Certainly not biased. No, that's all right. Yeah. I mean, it would, but there's a difference between being full-time and part-time. There, our system here, the Valencia, you are considered full-time when you have this many credit hours and above. You're considered part-time when you're this many credit hours and below. So, I mean, that's not bias. It's just, yeah, just a little status. No, they are statistics because they're a sample of the students. Okay? And then it wants to know which symbols would you use. So the 11.2 was the mean of the sample. English letters. Yes, the X with the bar above it, right? X bar. There you go. And then what's the 1.6, which was the standard deviation? That's the S. Use those English letters, absolutely. There you go. English letters. No Greek. All right. Number 18 is from 9.2. 9.2. Okay. All right. So it says the distribution of scores on a certain exam is N 70,5, which means that the scores are normal. And the mean is 70 and a standard deviation of 5. Sketch the curve and label the axis. The position of the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard, and plus or minus 3 standard deviations. So which picture represents that N 70,5? C, right? Because the mean has to go in the middle. So that's our mean. And then everyone else is going up by 5s according to that standard deviation, because that is a distance of 5, and so on and so forth. Absolutely. So it is C. All right. So now it says find the probability that a randomly selected score will be greater than 75. Shade the region under the normal curve. Okay. Well, we could talk about the region under the normal curve. Which one will it be? It's got to be B, because we want to be greater than 75, right? Okay. Now the question is, how do we find the percent? What can we do for this? It says something about the empirical rule. We can definitely do that. But what else could you do? Label the chart. Yeah, we can actually do that. But where else could we go? StatCrunch, right? We can run this kind of information in StatCrunch. Where would I go in StatCrunch? Yeah, right? Stat, calculator, normal. Put in our information, right? So, what was our mean? 70. What was our standard deviation? 5. And we want to be less than or greater than? Greater than. And what number? 75. Says round to 2 decimal places. 16, right? There you go. There you go. Whoops, dropping the pen. Picking it back up. 16. And what's the percent? So it is 16%. Now, the other thing that you could have done, and again, thinking about your empirical rule. So if we are between 1 standard deviation, how much was this? 68, right? So cut that in half, and that's 34, right? So this is 34%. So you've got half plus 34. Which gives you 84. Subtract that from 100, 16. Yeah, you could do that too. You could also take the 50% that's up here, subtract off the 34 that we know is covered. There you go. Yeah, we don't care about the other side, right? Yeah, Ron, absolutely. Lots of ways to think about it. All right, number 19. Number 19 is coming from 9.2 again. So same kind of question. Coming from 9.2 again, just like the last question. So it says the distribution of the scores on a certain exam is N30, 5, which means the scores are normal and with a mean of 30 and a standard deviation of 5. So which graph, A, B, or C, shows the N30, 5? A. Because again, you can see that 30 is right there in the middle, and then this is going up by 5s. Okay? And then they want to know, find the probability that a randomly selected score will be between 25 and 35. Which picture down below shows between 25 and 35? A. Because it's a between one, right? And so those are one standard deviation apart. We just talked about this. 68%. Using that empirical rule. Or again, you could go into StatCrunch and do that as well too. So let's just show StatCrunch real quick so we can show the between aspect. So this time you'll want to hit between. And then we change everything up. So our mean was 30 this time. Standard deviation still 5. And we wanted to be between 25 and 35, right? And compute. So you can see your 68%. Okay? All right, almost done. Number 20. This guy is coming from 9.1. And again, you can see it's about parameters and statistics. So the mean age of all 2,538 students at a small college is 22.8 years with a standard deviation of 3.5 years. And the distribution is right skewed. A random sample of 3 student ages is obtained and the mean is 23.3 with a standard deviation of 2.7 years. Complete the following parts. So, they want to know who is mu. Yeah, the mean age of the whole school. Okay, so that's your 22.8. Who is sigma? The 3.5, because that's your standard deviation for the whole school. Okay? Who is your x bar? Because that's the mean age for our sample of 3. And then who is the standard deviation? 2.7, because that is the standard deviation for the sample. Okay? So there's that piece. And then down below, is mu a parameter or a statistic? Parameter, right? So it's a parameter. And it's because it is found from the what? Population. Greek letters are always about that population. All right, now, one more question. Are the conditions for CLT fulfilled? They are? Okay. Yeah, the answer is C, no. No, they are not filled. Remember, your sample size has to be huge. It has to be bigger than 25 or normal. Okay? Is our population normal? Do we know that? It says it's right skewed. So it's not normal. So then we know it's not normal, so then we have to look at the size of our sample. Our sample size is how many? No, how much is our sample size? 3. That is not bigger than 25. No. Your sample has to be bigger than 25. What you guys were looking at, that 2538, that's the entire population.
That's what messed me up. I couldn't see it.
Yeah. Yeah, be careful on that. Remember, when you're talking CLT, now we're talking about your sample. Okay? Not the population anymore. All right. So then they ask a following up question to that. What would the shape of the approximate sampling distribution of many means, each of these, or each from a sample of 3 students be? And it looks like I might have deleted something, or she might not have put in the right information. Because there should be 4 choices. Will it be normal, right skewed, left skewed, or the shape cannot be determined?
Oh, they just like written together.
It's all right. There we go. So will it be normal, right skewed, left skewed, shape cannot be determined? What do you think? Right skewed. Why? Because the original one was right skewed, right? The population was right skewed. Why wouldn't our samples, if we kept doing it over and over again, not be right skewed? Because we know it can't be normal. Population ain't normal, and our sample sizes are not normal because it failed CLT, right? Okay. 21 is from 9.3. 21 is from 9.3. So it says a random sample of 10 colleges was taken. The mean rate of graduation within 4 years was 43.4% with a margin of error of 6%. The distribution of graduation rates is normal. So that's pretty important for us. So that means we know CLT should be okay. And so choose the correct interpretation of the confidence interval below and fill in the answer boxes. All right, so let's talk about this. Confidence interval. Which one do you think it is? C? You're close, but it's not C. So it is A. Your confidence interval, remember when you find the confidence interval, this is you estimating plausible values of the population. Plausible values for your population. In our case, it's population mean. Okay? You're using the sample to help you out with that. And I'm glad that you chose A and not B, because the 95% is not a probability. That 95% means that we are 95% confident that every time we would run this, we would end up with values that would contain that population mean. Okay? This 95% is never a probability. So anytime you see 95% followed by the word probability, it's gone. Cannot use that. It's not a probability. It's our confidence level. Okay? So then since we know it's A, we got to fill in. So we're between what 2 values? How'd you get 37.4?
I got the 43.4 minus 6.
You got it. Take your percentage minus the error. That will give you the lower value. So you said it was 37.4?
Yep.
What's the higher value going to be?
49.4.
Say it again.
49.4.
49.4? Because we take that 43.4 and add the 6% to it. There you go. So somewhere between here is our population mean. Okay? Everyone okay so far? All right, so then we got a question. Can we reject the population mean percentage of 26.3%? Can we reject 26.3% based on this information? Yes. Why, Rebecca? Because it's not in the interval. That's right. So we can reject it, which means it's either C or D. And which one is it? D? Very good, because it is not in the interval. Okay? And we don't worry about the sample size because we know that it's already normal. So that's why we throw out E. Okay. So 22 is also coming from 9.3. Pretty much same kind of question again. Same kind of question again. A statistics instructor randomly selects 4 bags of oranges, each bag labeled 10 pounds, and weighed the bags. They weighed 9.7, 9.6, 9.2, and 9.4 pounds. Assume that the distribution of weights is normal. Important for us. That means CLT is met. Find a 95% confidence interval for the mean weight of all bags. Use technology for your calculations. Answers part A and B. Well, first off, part A it says, choose the correct interpretation of the confidence interval. Which one would we be selecting? A, because it doesn't say probability or chance. Chance is another word that means probability. So, and it is about the population. Okay, so now we got to figure this out. So where are we going to go to figure this out? What are we going to do? Stack crunch, right? Okay, stack crunch. And what are we going to do in stack crunch? Where are we going to go? What do we got to do? We got to put in our values. We got to put in our values, right? Bags. So what were our bags? 9.7, 9.6, 9.4. Okay, now what? Click stat. Now what? So this is coming from chapter 9. T-stats, yeah. Chapter 9 is all about that. What do we got? 1 sample, 2 sample, paired. 1 sample. With data, with summary. With data. So select our column. We're not hypothesis testing, we're confidence interval, right? And then we're good to go. So now we have everything that we need. So it says your confidence interval should be to the nearest tenth, 1 decimal place. So what's our lowest limit? 9.1, tenth, 1 decimal place. What is our upper limit? All right, 9.1 and 9.8. 9.1, 9.8. Okay. So does this interval capture 10 pounds? Is there enough evidence to reject the null hypothesis that the population mean weight is 10 pounds? So does it capture the 10? No. So we know it's either A or B, C. Can we reject? Can we reject the 10 pounds then? Yes. Why? It's not in the interval. So which one would that be? A. All right, what's up, Antonio? Nearest 10th? 1000th. Sorry, I was looking at the wrong one. Wait a minute, we're on 22. Okay. So that was my fault. Nearest 1000th. So 3 decimal places. What would that have been? So let's go back. That was my fault. I was looking at the previous problem, number 21. 9.122. And the other guy? 9.828. All right, so let's go back and fix that. Good catch. 9.122, 9.828. Still, though, that doesn't change our bottom answer. You still, 10 is not captured, and we will reject the claim because it is not in the interval. All right. Number 23 is coming from 9.4. 9.4. A health agency suggests that a healthy total cholesterol measurement should be 200 milligrams per deciliter or less. Records from randomly and independently selected people from a study conducted by the agency showed the results in the technology output given below. Test the hypothesis and the mean cholesterol level, or test the hypothesis that the mean cholesterol level is more than using a significance level of 0.05. Assume the conditions are met. All right. So the first thing is they want us to know what is our null and alternative hypothesis. So what do you think? Say it again. E? Absolutely. Because your null hypothesis should always be equals. So that means right away you can throw out D, B, C. Okay? And then up above, it gave us the key words, more than. So makes sense why it has to be E. All right. So the test statistic is, based off our information, 1.26, because it says do not round. Okay? And the p-value is perfect. Okay. So since the p-value is blank, greater than or less than or equal to? Greater than. The significance level, because this is definitely bigger than 0.05. Okay? Blank the null hypothesis. Reject or do not reject? Do not reject. There is blank evidence to conclude that mean cholesterol is more than 200 milligrams per deciliter at a significance level of 0.05. Insufficient or sufficient? Insufficient. Because we didn't reject it. It's not enough evidence. Everyone good? All right. Number 24 is, again, 9.4. Coming from 9.4. In country A, the population mean for 3-year-old boys is 38 inches. Suppose a random sample of 15 3-year-old boys from country B showed a sample mean of 37.5 inches with a standard deviation of 3 inches. The boys were independently sampled. Assume the heights are normally distributed. That's important for us. So we know CLT is met automatically. And then parts A and C below. Complete them. So part A says determine whether population mean for country B boys is significantly different from country A. So which one of the following is our H naught and ha? Say it again. E again, absolutely. Because our mean was the 38, and we want to know if it is different. So that means if they are not the same. Did it change? Okay, so now we want to find our test statistic. So how are we going to start doing this? Stat crunch, absolutely. Let's go to some stat crunchies. And what are we going to do? Stat, check. T-stat, check. One sample, check. Actually, it's a summary. You don't have the data. We don't know all 15 boys' pieces of information. We have the summary of them. Okay? So, what is the sample mean for those boys? No, that was for the population. What's the sample? 37.5. What's the standard deviation for them? What was the sample size? Okay. And we're hypothesis testing. So what are we equal to here? 38. And then does our sign stay not equal, less than, greater than? Remain the same, right? The not equal. So there it is. Hit compute. Now we know our t-stat and our p-value. So the t-stat, it wants 2 decimal places. The p-value wants 3 decimal places. Okay? So what was our t statistic? Negative 0.65. And what's our p-value? 0.529. All right, let's go fill those in. Negative 0.65, you said. And our p-value was 0.529. Okay. So do we reject or not reject? Do not reject. So we got 2 choices, B or D now. So we're not rejecting. D. Because if you look at part B, it says there is no reason to believe in the 38 inches. But remember, our null hypothesis, we didn't reject it. We said it was 38 inches. Okay? So there's no reason to reject that. Okay? All right, now, it says suppose the sample consisted of 30 boys instead of 15. Yeah, go back to our StatCrunch, right? And then we can go into options and edit. All we want to do is switch out the 15 with 30. Keep everything else the same. And now here's what we have. So again, your t-stat is 2 decimal places. Your p-value is 3 decimal places. So what is our t-stat to 2 decimal places? Negative 0.91, good. What is our p-value to 3 decimal places? 0.369. So what was our t-stat again? Negative 0.9 what? 91. And our p-value was 0.369. So some of the question bled onto the back of this. So based off of that information, do we reject or not reject? Do not reject. So that means it's C or D. Which one is it? D? It's not going to be D. It's got to be C. Same reason as what we had above. Yeah, if you look at D, they kind of trick you a little bit. It says the reason to believe that, their reason to believe that 38 inches. So it's kind of saying believe in the 38 inches, but if you read a little bit further, is not the population mean. So they kind of like, you got to be careful. Make sure you read the entire choice. Yeah. C is the one that we want because it says the population mean is definitely 38 inches on the basis of the data, according to the significance level. Same answer that we had before. All right, one more question then. Explain why the t-values and p-values for part A and B are different. So, notice all these are talking about a larger n. What does the sample size do to everybody else? If I have a larger sample size, what will that do to the standard error? What will that do to your p-value? Say it again. They will decrease them, both of them. Because the larger your sample size, remember when we were doing this, all the formulas, when you do that standard error, have the square root of n at the bottom. The larger the sample size, the smaller that standard error will become. And when your standard error gets smaller, that makes your sample wider, which, will make your sample wider. And what will that do to the p-value? Sorry, not wider, narrower. Throw my makes the p-value smaller as well too. Yeah. So which one is it that we're looking at? The larger n causes what? C or D? D. So smaller standard error, which makes it narrower, with less area in the tails. Correct. The more narrow you are, the smaller your tails are going to be. Okay? Cool beans? All right. The larger the n, the smaller the standard error, the smaller your p-value. All right. Number 25 is coming from 9.5. Number 25 is coming from 9.5. Last question. So it says a random sample of male college basketball players and a random sample of male college soccer players were obtained independently and weighted. The accompanying table shows the unstacked weights in pounds. The distribution of both data sets suggests that the population distributions are roughly normal. Determine the difference in means is significant, using a significance level of 0.05. Let mu baseball be the population mean weight of college male. Baseball players. Let mu soccer be the population mean weight in pounds of college soccer players, male. Determine the hypothesis test for this, and then we'll start going through everything else. So there's our data, baseball and soccer. Okay, so what's going to happen for our H naught? Is it going to be not equal, greater than, less than, equal? Equal. H naught is always equal. Now, they want to determine that these are different in means. So are we going to be not equal, greater than, less than, equal? Not equal. So there's what we know. Now we need to run the information. How are we going to do this? Stat crunch. And it'll be a little bit easier for your test. Unfortunately, we have to go in and we actually have to put in all this data into our stat crunch. So this will just take us a couple more minutes longer than what it would taking your actual test. So let's put baseball in this first one. We'll put soccer into the second one. All right, start feeding me some numbers. Oh, hold on. 200, 190, 183. Okay.
206, 188, 183, 211, 229, 229, 230, 197, and 171.
There's more.
189 for baseball, 210, 201, 185, 187, 194, 204, 196, 187, 199, 192, 188.
All right.
169,
Oh, hold on. Okay.
96, 189, 188, 186, 191, 172, 186, 172, 183, 170, 196, 185, 157,
Hold on. 185, 157.
171, 178, 164, 153, 177, 185, 186, 177, 196, 158, 163.
Perfect. All right, so now we got our data in. Now what? Stat.
T-stat,
T-stat. To sample. And this is not paired. Okay? So be careful. There might be a paired one on there. But most likely, since this one's not paired, I don't think the other guy will be paired. So to sample with what?
with data,
With data. Who's column 1?
soccer, baseball,
Baseball. Who's column 2?
soccer.
Soccer. Is this, information correct for our hypothesis? Absolutely. Compute. Now you know everything you need. 2 decimal places for your T. And says 3 decimal places for P. All right. So what is our T-stat? 4.91. What is our p-value? 0. Yeah, 0.000. There we go. So let's go in and fill that in. You said the T-stat was 4.91, right? And our p-value is 0.000. All right. Blank H naught. Reject or do not reject? Reject it. Reject it because this number is less than our significance level, the 0.05. So at 0.05 significance level, they're blank, sufficient evidence to conclude that the difference in mean weight is significant. There is. That's it. That's what your final will look like. Chapter 7, Chapter 8, Chapter 9.